Good morning to everybody to my channel Smart Polist. That is a small description about myself. Polist model from NIT Bhugapur, MTech from 2016 to 18, and is the communication mail address polistmodel351@gmail.com. In these sections, it will be a series of lecture videos. In these video lectures, I will describe you some of the things whatever I did in my project. In these sections, I will broadly describe about my all the project that anybody can be tech student as well as MTech student as well as PhD students also can take to the project for their academic. Here in these sections, I will describe about the basic thing of particle sum optimizations. Those who are the students are very interested to soft computing, neural network, deep learning, machine learning, can continually follow my videos and lecture videos. That will obviously gives you a better understanding and better views. Let me discuss whatever the topic I will be covered in the series of lecture video. First one will be PSO, particle sum optimization. I will be covered in broad areas. After that, I will cover the neural networks. Neural networks I will be covered. After that, I will cover benchmark dataset, dataset and data training. Data training in neural network. After that, data training in PSO result, and after that I will cover the result. This will be covered into one by one sections videos. These things, if you continuously studies these things, they will might be give you some better understanding and good view and good results of your academic project. If you have feel any problem, you will communicate with me via my mail. If I will free, I will give you satisfactory result and I will give you the future work of this project if you can take. And I will discuss all the things with the logically, theoretical and coding section also. I will cover the coding sections in MATLAB environment because it is easy to understand and implementation. Let's get started with the very first topic about particle sum optimizations. Let's start with the particle sum optimizations. Before that, what is particle swarm? Let me see some picture about here. Particle swarm optimization. In a swarm, there may be the particle or can be fish or can be bird. See, there is a school of fish, those, and their movement. How they will movement, it will depend upon some of the logic behind. In this logic, the particle are moving from one directions to another directions, from one position to one other position for searching food or for survive themselves. It is about the particles. See, in the school of fish are going from the particular directions. Here also see, the school of fish is going from the particular directions for searching the food or something else. It is the best example. So also, the school of fish are coming in the that direction, particularly in these directions. So, in case of birds also, the bird is walking from the one positions to another positions or flying one position to one for certain condition of searching food or for surviving themselves. So, how they will fly, what is the velocity, what will be the directions, what will be the positions of the what will be the movement, all the things is logically depend upon. It is the best example. See, suppose in these directions, each of the particle here in case of uh, birds maintaining some rule and they will not divert from the swarm domain and within the search space. We'll come to the broad discussions one by one. Let's give me some example first. Suppose in your house, in front of your house, suppose in the very early morning, you'll maybe notice this thing that suppose you here, okay, suppose you are here and you are spreading some foods you spread some foods here, nearby areas locations. You spread some foods. You will see after a few times some birds or crow will come take the food. Obviously, suppose if bird is came, a bird is came. After that, if this bird will try to make some sound to call the another bird. After that, you will see another bird is coming from the far away. When the bird is come to the very close of the foods, okay, bird is come very close of the food. This birds also crying, or this birds also making sound to call the others bird. What happened after few minutes? Number of the birds will come to there to search the food or to take the food. Okay, in this way you can see within few minutes number of bird or number of crow will come to take the food. It is about the example of bird. If it's not there, I mean bird is not there, maybe it is the possible with the very common example with ant. In a house, if you spread some molasses or sugar in a particular position or sweets, you will see if a single ant can find the sweets that is in a particular position, after that number of the ant will come to take the sweets. But how they will come, how they will communicate, we need to understand. So now I'm going to the another examples which is very similar to the particle soft optimizations. Before that, let me give some basic introductions about the particle soft optimization. Particle sound optimization is a swarm intelligence system. It is first developed by Dr. Russell Earhart and James Kennedy in 1905. It is inspired by the school of fish or flock of bird. And there have a paper, the basic ideas or concept about particle sound optimization. They are trying to which how the particles are moving and the social behavior. From this inspirations, particles from optimizations concept is came. So it is about the particles of optimizations. So now we'll go to the another sections. We'll obviously go to the another sections where we'll give the idea about the particles of optimizations. Okay, suppose let's say two friends went together in a hill, okay, to find the which hill is highest. Like this hill. So suppose 2%, suppose a percent P1 and another percent is P2. They went together. Suppose P2 is standing here. P2. The person is going to search the which mountain is the highest. They don't know, but they have some measurements. They can and measure the distance from where and the surface area, I mean water surface area level they can stretch. In this way, suppose we measure the surface area of something and P2 also measure the surface area of something. After that, they communicate to each other. P1 and P2 they communicate to each other and which surface area is good. I mean which is the very highest, and they come to the decision that P2 is the highest. After that, P is not getting the very highest monument. So what will happen? P2 P1 will move to the another mountain. Suppose P1 found another mountain here, and this is the highest mountain. There after that they will communicate to each other, and after communicating to each other, they come to the decisions that P1 where P1 is now is the highest mountain. Okay, so obviously to see the highest mountain, what will happen? Sorry, to see the highest mountain, what will happen? What will happen? P1 will goes to the another mountain, P2. Now P2 will come to the this mountain. Suppose P2 come to this mountain, and after that they will communicate. Till now, what happened? P1 is the highest mountain. Okay, so what will happen? P2 till now not getting the highest mountain. So P2 will shift it to another mountain. Suppose P2 will go into this mountain. Now what will happen in this case? Which mountain is highest, P1 or P2? Obviously P2 mountain is highest. So what will happen? P2 will communicate with the P1 and he will come to the decision that he is now in the highest mountain. Okay, highest mountain. So obviously to find the highest one, P1 will not stay here. P1 going to forwards to find the highest. After that, P1 come to here at this mountain and taking the distance, and he come to the decisions that he is now in the highest mountain ever after communicate with the P2. So P2 will goes to the next mountain. So if P2 will goes mountain, P2 will go to here, and it is not, but that P2 will go to here. It is also not highest than P1. After that, here also it is a not highest rather than P2. So in this case, we will find the highest mountain. P1 get the highest mountain. P1 get the highest mountain here. Okay. Now how P1 come to this mountain? Any idea? Obviously, they come to this idea. There is some basic logic behind there. What is the logic? They come to in this logic via communication. Communication. They make communication first, and from the communication, they learning and their movement and the movement. In this scenario, they will come to the decision that they are in the highest mountain. Obviously, these three components will take the decision that P1 in this P1 is the highest mountain. P1 is the now highest mountain. This positions P1 is now in the highest mountain. So they coming to this decision. In this scenario, they come to the decision that P1 is the highest mountain. So this is a communication plus from the communication they learned something and they moved to find the best solutions. That's why they get the exact value or the very high monument or high mount ever. So this thing is applicable in particle sum optimization also. In particle sum optimizations, what's happened in the particle? Suppose in the case of this thing, so suppose they are moving from one direction to another direction. Suppose this thing are going to another one direction to another directions. Let's talk about a particular things. Suppose there is a PSO, I think. Okay, so in this case, they're going from one direction to another direction to find food or to survive themselves. So how we go to reach the optimal solution or to the exact position? How they will go? The question is where. So everywhere they're moving some forward directions, and after that they will communicate, and after that if need they will change the direction, and by this way in this one suppose in this color picture this one, in this one each of the particles will communicate to each others and they will change their direction, the velocity and the positions according to the times. For each of the time seconds, they will change their velocity positions, the components, whatever they have, to reach to the global solution. Suppose the food is here, so it goes to the food, everybody will trend toward that directions. It is a particle swarm optimization's best idea or the best example. Now, I will go into the forwards of the particle swarm optimizations, and I will, along with that, I will make a diagram of a particle swarm optimization in eDrawmax. Let's say it's the eDrawmax. You can draw it in eDrawmax also, no problem. So in the particle swarm optimizations, I will uh, try to make a diagram of the particle swarm optimizations. The exact diagram you can do the same, so and that is not copy pasted anywhere. Okay, it is myself own diagram. So let's start it. Suppose for a starting positions, particle have a positions here. Let's get the particle positions. Let me make it large. Okay. Suppose it is a particle positions. So in the particle positions and the particles in these positions, I will I make number of the copies here, but we need it later. Suppose it's the particle positions. So let's write down the particle positions. It is the particle positions. Okay, and the particle positions, it is described by here. We are trying to take another directions here. Text here, particle positions. Particle position. Suppose it is the particle positions. Okay, it is the particle positions, and positions is let me x tid x t we make to it tid x tid. Okay, we will fill the form this next time, not now. So it is a particle, suppose it is particle position first. So it is the whole thing in this swarm space, and swarm space it is in the particle positions. Suppose the in the swarm swarm is trying to move from this direction. Suppose the swarm is trying to move in this direction. Okay, suppose this swarm is it is arrow. Let's see the arrow how it works. Suppose this swarm trying to move in that direction. So in the particle position. Okay, so in the particle position, suppose in this swarm space the particle position will not be here. The particle have the another position. What is the particle another position? Let's see, the particle position is will not be here, particle position will be here. Okay, particle positions will be here, and it will be the particle best positions. It will be the particle best positions. So write down it will be the particle best positions. In the next iterations, suppose it will be the particle best position, but and in this one space, if the particle is going to that directions, so obviously this one will be the particle global best position. Obviously this will be the particle global best position. The particle is moving from that direction to there. Okay, It is the particle global based positions. Or for changing the picture, let me draw it here. Okay, particle global based. Global based. It will be the particle global based. Suppose. But what happened instead of the particle going to that direction, instead of particle come to the particle rest position, the particle is moving here. Suppose here, particle is came to here. Okay, particle is came to here, and particle is in new position. This is a particle new position. Okay, this is a particle new positions. Maybe it is happened. Now ejecting the this thing. The particle position is here, particle best positions is here, and particle new position is here. Okay, why is it like that? Because obviously every time the particle position is here, from here to you will directly go to the this position is not sure. Maybe it will next iteration will be goes to that here or any some other place to, for the simplicity. Take assumptions like that, it will come to this directions first. Okay, this directions come to it is a come to the this direction first. Maybe happens, and particle new position will be there. Instead of going there and there, particle is come to the directions here. So let me connect these things with a dot lines or a line. So what will happen? So particle is the particle, it will be goes from its current positions to the new positions. Suppose it is goes from current position to the new positions. Okay, this is true, and each of the particle have their velocity. And suppose the particle velocity is this direction. Maybe possible particle is moving to that direction. Average velocity in these directions. It is possible. So what happened? Now the particle, what happened? Particle will go first from its best positions will be the this directions would be that, but instead of going it is going to the another directions. Particle will be goes to here, obviously here. Instead of going visions here, and another one is why I will make different line here. I will come to the sections later. Okay, so it is a velocity component. Suppose particle velocity component, it is a velocity component. Velocity component. Velocity component. Now this is a velocity component of the particle in this direction. So why we will make the different? So particle velocity component is the come that directions, and it will shift it to particle previous position to the next position is here instead of going rather than this position or this position. Now take me some basic values of the parameters values, whatever their content. After that, making these things, I will come back to very soon here to make the things. Yeah, I'm come back to again here. Now the description here that the particle positions is the previous positions. Okay, so the particle position is this one. Let me fill this particle positions with like this color. Okay, so it's the particle positions. And the particle positions of xt of id is the surface position, t is the particle position. From here, it is the particle position is here. So I will fill the color with the same colors, I think. So it is the particle new positions here. Now this position the new positions, and particles have the best positions here. Instead of going the particle best position, is come to the another positions to make it color another and p best. P best is it a p t of id is a particle best position, and particle new position is pointed out by particle position previous position plus t plus 1 is the new positions, and the particle best positions I will fill it out with another colors like with these colors. Okay, it is the particle global best position, and particle velocity is like this component type. So what's happened first? So we will calculate the vectors of the all. So what will happen? This vector it will happen for this vectors will happen is like that. First C and sorry Z of yeah yeah. So this C and this positions will be like this. So it will be the final positions minus its initial positions. Initial positions is this positions. Okay, so this position. So it will be the equation for that. Okay, like that particle new positions equations will come to the letters, and it's a particle global best. So what will be the equation for particle global best? So it will be the positions of the same, and sorry it will be minus, and for that its initial positions in this position. Okay, this positions it is a comparative. So what happened? Let suppose a particle this particle is came from that directions. Let me the fill color with the this. Suppose coming it's in that direction. After that it goes in that direction in particle best position. Why it is coming in that direction? Because it is depend upon its previous positions. So according to the previous positions, the particles is goes first on this velocity component along with that in that direction. After that, this particle again move to the another directions to its best position directions along with that. Let me describe. This goes to that direction. Goes to that direction. After that, what happened? The particle from this position states went to the new position. This understands? Now what happens? It's the clear picture of particles of optimizations. Basic diagram of particles of optimization is a clear diagram. So it is first goes towards previous positions along with that directions. After that it changes those positions and it goes towards its best position directions. After that it goes towards the global best directions to the new, and it is reach here and this is the new position particle. So what will be the particle new positions? Particle new positions here. So we need to calculate here the particle velocity. So velocity will be like particle came from that direction. Okay, so it will be the velocity component vt plus it is goes to that direction, and this direction is very parallel to the particle dispositions. So plus add with this component, plus it is goes from there to here. So this component is very parallel to the particle global velocity, so we'll add this component. So it will be the particle velocity, the velocity from here to here or here to here. So it will describe me in the next slide. In coming lecture, describe me again particle previous positions to come east, that direction according to east previous positions, then it goes to this dash direction position along with that directions. After that it is come to the global base position along with that directions, then it is the particle new positions, and these vector component summations is the particle velocity, and particle velocity will be vector component v, this component plus this component, and this component is parallel to that, so it will be added with this, plus it will come to here and it will be added with this. So it will, I discuss these things. It is a basic diagram of particle sum optimization you can draw and you can use in particle sum optimization directions, and we will show the equations in PowerPoint slides. Now particle, it is a particle actually new velocity. Let me copy these things and if possible, so let me paste it here. Particle velocity, this one, yeah, whatever this one. So particle velocity, what will happen in the particle velocity, this will be the particle velocity. So it will be the particle velocity. Particle velocity will be like this. Why it's like this? Particle new velocity will be the its previous waste component, as I told, this plus c1 rand. What is this? I will come to the lectures. So here we need two modifications, because see in this equation, so when it is goes to that direction, this and this direction is not similar. Direction is similar, but the component length is not similar. So in this path, particle have maybe some acceleration, and maybe in that direction have particle another acceleration. For that purpose, we take two random number of particle acceleration as c1 in this component as well as c2 in that component, and along with that we used a rand. Rand is a random number between 0 to 1, and here we use another random number whose value between 0 to 1. It will be the particle positions. In this particle positions, if the particle is came in along with that direction, is not exact value will be that, maybe we need some modification here. What is the modification? We should have to use some value here, that is called omega. Omega we need to add here. Let me insert the values of omega. Sorry. We need to add here some value of the omega here. If it's omega there, so I will use my others. I will use the another thing. Omega. Okay, that's fine. So omega will be placed here. Okay, why omega will be placed here in these positions? The reason that when it comes to its previous positions, the value is not be the same. So that's why we using the omega to modify its velocity along with the previous positions, and the omega have some boundary value, some upper limit to the lower limit, and c1 have the value, maybe any value, and the rand is a random number, so it is a particle velocity. Now after getting the particle velocity, this equations describe the particle new positions. is particle new positions. In these positions, it will describe particle new positions. How? When you get the particle new velocity of this one, so new velocity added with the particle previous, it will add it with the particle previous position, and it will give the particle new velocity. This equation will give you particle new velocity, new positions. So it is a complete equations about the particles from the optimization with velocity sense as well as new positions. From these equations, now we need to know some terminology. In the first terminology, whatever is there, this terminology known as a inertia term. It's called as a particle inertia term, this thing. And after that, this component up to here, this thing, a particle, it is known as a particle cognitive term is this. After that is a social component or social term is known as the third one. This one is this social component. Yeah, these things we need to know. The first one is inertia component, second one is cognitive component or cognitive behaviors of the particles. It will not be the plus value, sorry, and it is a social component or social term, or cognitive component or cognitive term, social component or social terms, as you wish. It is a basic particle swarm optimization. Its value change, particle position value, updation value, aggregations. Let me discuss all the things along with that side again. So this one, particle new velocity, and this one is the inertia term we are using to with the velocity component to manage the boundary velocity of the particles, and it is the particle previous velocity, and it is the C1 is called as the acceleration coefficient, as well as C2 is called as a acceleration coefficient. In this equation, rand is a random numbers value within 0, 1 to 1, and it is the particle best positions to particle positions component value, and it is the particle global best position to particle positions values component value. And this equation particle is this equation describe that it is a particle new positions, and particle new position is the particle previous positions plus particle new velocity. And this equation, this one is the inertia term, this is one is the cognitive component or cognitive cognitive component, and this is the social component, and another two things is there, whatever sorry, control V, अच्छा अच्छा inertia term as omega, this omega, okay, and acceleration coefficient is C1 and C2. Acceleration coefficient is C1 and C2. This is known as the acceleration coefficient. Oh, okay. And rand is a random number. Okay. Number in between 0 and 1. Sorry, 0 and 1. In between 0 and 1. Okay. It is about all the particle swarm optimizations. First lecture video is up to this. After that, I am going to the coding of particle swarm optimizations. Thank you.